And after that, everything is history. So he's now is well known as the first person who used a telescope, and everybody knows his name. But that was not enough. We did not stop there. We made more and more telescopes, and slowly over time, we have now reached a stage where our telescopes are much bigger than our own size. In fact, Ayuka has a telescope here close by to Pune, which has whose if you say, let's say, telescopes have lenses, or these days they have mirrors, and the mirror itself is bigger than me. It's 2 meters wide, okay, and and the telescope itself is 3 stories high. I'm not talking about the GMRT. I'm talking about the Ayuka Giravli Observatory, which is also very close by to the giant meter wave radio telescope, GMRT, which is another huge giant telescope, one of the largest in the world. Okay, so come from that humble telescope which Galileo could make, and in fact, actually, you can also make. If you're interested, let your teachers know. Ayuka can help you make your own telescopes, small telescopes like Galileo did, and you can do your first basic observations with it. But we are back, that we are talking about the modern telescopes now, and I'm going to talk to you about 2 very special telescopes that have gone beyond these earthly telescopes. Now we were facing some limitations, and because of that, we have put some telescopes up in space. Okay, and that's where astronomy and space science joined in, because astronomers know how to make telescopes and how to use telescopes, and space scientists know how to put them up, right? So that's how ISRO joined hands with the Ayuka and many other institutes, and we actually have a telescope called AstroSat up there in space. But there are many other telescopes, and I will tell you about them and what they're doing. However, I always make my talks or whatever, these interactions, in such a way that you can learn something and you can probably get ideas to do something. Okay, so let's see. I will be talking about something special today, and in scientific terms, it's called the spectra. Okay, so have you heard this word spectra before? I can see some people, maybe they can nod their head and tell me whether they've heard this.
No, sir.
Okay, so spectra is a plural for
band of 7 colors.
Spectrum. Yes.
Is the band of 7 colors.
Yeah, the spectrum. It is spectrum.
Okay, good. So that's enough. That's good. I understand that you can relate to what I'm asking about and what I'm going to be talking about. So as you can see, the name of the talk would be not just spectra, but astronomical spectra and space telescopes. You think, what is this person?
Hello. So you are not audible.
Seriously?
Yeah, now.
Thank you. I'm sorry. I somehow went on mute. I don't know. Maybe you tried to mute everyone. All right.
Maybe.
So anyway, just don't worry. We go on. We are in a space age, so these things happen. So we in astronomy we talk about planets, right? And this is an amazing picture of a top view of Saturn, where actually one of our spacecrafts has actually gone there, right? Beautiful picture. We also have through other telescopes pictures as lovely as this. So you can see this is a picture of something we call nebulae, okay, or nebula actually. For singular, it's one nebula. Multiple would be nebulae in Latin. So this is a huge cloud of gas, okay, And it looks colorful, but there are reasons why it looks so colorful. And there are various kinds of gases which are there, like oxygen, nitrogen, etc., which are emitting this light, which you can see through your telescopes. Okay, very faint light, but your telescopes allow us to make it brighter and bigger and more detailed, the picture, and we can see these things. Okay, then I'm sure you've we can see stars, right? So with your naked eyes or with binoculars, etc., stars, they look like tiny points of light in the sky, right? And but with big telescopes or the mega telescopes that we have these days, and good cameras to actually capture the pictures for a long time, so you can collect as much light as possible through your telescopes and store them to see it later. Okay, and that can give you amazing, mind-blowing pictures like this picture of a cluster of stars. Okay, this is a cluster of stars. Our sun is a single star, a lonely star. Okay, and thankfully it's lonely, because you see, even during cloudy days we feel hot sometimes, right? In the summer it's extremely hot for many people across India. Just imagine if there were not one but two suns in the sky. That would be unbelievable. In fact, I don't want to even think of it. Just imagine now if you were in this system. This is called the Pleiades cluster, or in India it is known as Krutika. Okay, the 6 sisters. And this one has so many stars around one place. So if you're an unfortunate planet which existed here, I don't know, you'd be boiling. Okay, so but then all these things are visible to us through telescopes. Then we have much bigger collection of stars which are called galaxies, and this is a amazing picture of the Andromeda galaxy. Okay, Andromeda galaxy is one of our closest galaxies, but even then it takes light about 2 million years to come from that galaxy to us. Okay, so this picture that you see here, the light that you see which has made this picture, actually started about 2 million years ago from there. And we are seeing it now. Okay, so this is the closest galaxy, which is still 2.2 million light years away from us. And then there are other galaxies which are farther away. And there are single galaxies, like our sun is alone. Therefore, the galaxies are much bigger. They are collections of billions of stars. And even galaxies have sometimes groups. Okay, and there are collection of groups which are called clusters, and these form kind of the basic units of the large scale structure of the universe. Okay, and I'm just giving you these pictures, showing you these pictures, so you don't confuse between what is the solar system. It's just made out of our 8 planets and dwarf planets and some asteroids, comets, and the sun. But this one system, solar system, is a tiny thing in a much bigger thing which has, hundreds of thousands of these kinds of systems, which is called a galaxy. And there are billions of these galaxies which make up the whole universe. Okay, so that is the kind of thing which astronomers study. Okay, the universe, which is unbelievably big. But again, as I said, we are smart people. Okay, so are you. You are also very smart people. So you are able, over time, we have been able to make these devices which allow us to see things which are really far away and really old. Okay, so that's what an astronomer does. Now, just stop for 1 second and think about who or what kind of how does this information about these galaxies and other things come to you. Okay, so let's say you're talking about me. Okay, you're talking to me right now. So what are the sense organs on your body which are giving you information about me? First thing, you are looking at your screen, so you can see me, right? So it's light which is coming to you. I'm also audible to you. You can hear me. Okay. And suppose I was lucky enough to be in your classroom, like your teachers are or your friends are, you might be able to even say hello to me, shake my hand, and actually touch me. Hopefully I would be smelling good also. Don't worry, it's a bad joke, but you can also kind of smell things and get information about that. There are other things like food which you can actually taste also, and that also gives you some other information which your nose cannot give or your ears cannot give, right? So this is kind of a complete information for which you use all your sense organs. Okay, but now let's say I ask you about the closest astronomical body to the Earth, which is the moon, right? So what kind of information, in what way does information come to you from the moon? It can only come in the form of light. I don't think anybody has ever, gone on the moon and tasted it or smelled it, etc. Some people have landed on it. So of course, that's there. But if you go to, let's say, Mars, not go to, but if you take the example of Mars, then you will see that information from that only comes in the form of light. Take any other faraway body, only way of getting information is light. Okay, so we can just see it. So you can see how astronomers are very, very limited in the way they can get information about the universe. But even then, there is so much that they can tell you. So I'll tell you one way in which smart astronomers, which one of you can also become, find out details about the things in the universe. And it's not just about structure and color, but there are many other things which they get by using the light that they get smartly. Okay, so they have to understand the light completely. And let's say in the next half an hour or so, we'll work together on trying to understand some properties of light and then how astronomers use them. Okay. So another thing that you can only get information about through light is a rainbow. Okay. It's a wonderful thing, and it's a rainy season is still continuing for a long time in Maharashtra. So I'm sure you must have caught a rainbow or two at least during the whole season. So rainbow, as some of you are saying, yes, spectrum, it is actually a spectrum. Okay, and some of you said that there are 7 colors on it. Okay, now do look at the rainbow properly, and if you see it, yeah, maybe you can say there are these colors there. Okay, now you see a rainbow, but it's not from the rain. It's it's from this glass thing called a prism. Okay, and you can see that a white light has come from this direction, and there is a band of various colors. Okay, maybe here you can only see 4 colors or something. I don't know, depends on how good your eyesight is. Okay, but just for our convenience, we have named them in some bands of light that our eyes tell us are red, orange, yellow, green, blue, indigo, and violet. Okay, so this is the these are the names of the major colors that our eyes can differentiate. But of course, if you look at a spectrum even better, okay, the visible spectrum. So the scientists actually call this the visible spectrum because it's visible to our eyes. And you'll later ask, what is this? What is invisible spectrum? So we'll talk about that. But let's first deal with the visible spectrum first. So these colors are actually, if you look at actual spectrum, this is a picture of an actual spectrum. Okay, and if you look at it, because in a picture like this or in the rainbow, you cannot like zoom in and try to see details of it, and that's what scientists do. They want to observe everything even better and better and better. Okay, so this is a picture of the visible spectrum, a spectrum just like it, taken with a prism, and the colors have been spread out by a process called dispersion. Okay, so dispersion is something which splits light and gives us this kind of a spectrum. Okay, So in this, if you note it, and if you can maybe bring the screen closer to your eyes, then you might see that there is no place where the red finishes and the orange starts, and the orange finishes and the yellow starts. There's not like a block. So if you draw a rainbow with crayons in your arts class, you will use 7 pastels and then 7 crayons, and then your rainbow is done. But the real rainbow is not like that. Okay, it's not made out of 7 exact colors. It's made out of this combination of colors, and it's all a continuous stretch. Okay, so there is no like break where this is yellow is finished. Okay, now there's a black line, and then this other green is starting. It's not like that. It's just a continuous stretch. Okay, and the rainbow has that. Any other spectrum that you see with any other thing, like you can use a glass block, or even I think if you have a scale like this, which is made out of plastic, you see it has a slight edge, slight slanting edge. You can use this with sunlight and get like spectra as well. Okay, through dispersion. So there you can study that, and it's not like broken up into pieces. So when you grow up, you will come to know of other properties of light, like it has a wave nature, and therefore it has a wavelength and frequency, etc. So if we talk about the wavelength, so the spectrum is actually a combination of different wavelengths of light. Okay, and so they go from the wavelengths though are very tiny, very small. Okay, and what is written here on this scale that is measuring the light is nm, small nm, which is nanometers. Okay, nanometers means the millionth. When you go to millimeter, it's the 1000th part of a meter. Okay, then you go to micrometer, which is the 1000th part of a millimeter, and then you go to nanometer, which is the 1000th part of a micrometer. Okay, and so these are around these wavelengths of light, which are around say 700, close to 800 nanometers to 315 nanometers. These are the wavelengths of light that our eyes are sensitive to. Okay, these are the ones that our eyes can see, but that does not mean we see everything. Okay, so we are limited. Our eyes are limited to seeing this range of colors, this range of light, actually, which we call colors, and it's called the visible spectrum. But there are more things beyond this side, on the higher side of wavelengths and lower side of wavelengths, which we'll not get too much into, but I will tell you they are there, and they are also important to know about. Okay, so so we can split light. Let's understand that. So we can split light, and I have told you one process of splitting light is if you pass white light through some denser medium, from a rarer medium to denser medium, and back it actually spreads up into this what we call vibyur, but it's actually a continuous distribution of colors. This is called dispersion, and you may have come across this term in your school. Okay, or you may come across it soon. So there is another way of doing it, which was discovered not too long ago, and it is called diffraction. Okay, now diffraction can also give you some such spectra. Okay, as you can see, this is one spectrum, this is one spectrum. Now this one and this one are ulta. So both their violets are close to each other. Okay, and reds are farther from each other. And what is happening is, in this case, white light is not passed through some medium, but it's passed through a narrow gap. And narrow means very narrow. In fact, it could be like, smaller than the width of your hair. Okay, if you actually pass white light through a very narrow gap or a sharp edge, close to a sharp edge, you can get this phenomenon, which is called diffraction. Okay, it's not dispersion, it's not refraction, it's not a combination of both. It's a separate phenomenon called diffraction. Okay, and so this is another way of splitting light. I am sure if you're not able to understand this, just keep it in mind, because sometimes we can keep something in mind and later find out more about it. Okay, so later you'll not be lost on what is diffraction. You know the application, but you'll understand it later. So diffraction happens, as I said, around some sharp edge, okay, or with a small gap. So if the gap is really wide, okay, light as a wave, if it comes in through and tries to go through this gap, it will form another kind of a wave pattern here, okay. And if the gap is there, it shows more of a wave form rather than when the gap is wide, okay. And there's also a dependence on the wavelength, okay. So this curvature that you're getting, it's, let's say, just for your understanding right now, is we can say that it is the measurement of the diffraction that is happening. So narrow gap is very important, okay. And for large wavelengths of light, the diffraction is large. For smaller wavelengths of light, the diffraction is less, and that's what gives us this splitting, okay. Here also, in dispersion, you will realize that the red, which is the higher wavelength, right? You remember that higher wavelengths in the spectrum. Reds are the higher wavelengths, blue, greens are middle, and blues are low wavelength. Okay, so the red tilts less from its original path, and the blue tilts the most. Okay, and here also there is a rule like that, and so because different wavelengths are there in white light, but because of diffraction, they are made to separate from the original direction, but they separate all in a different way. Okay, so with a different angle, so therefore they get spread out, okay, in diffraction. In fact, this is a example I found on Google Maps where there's just plain waves of water coming from far off, and there is a place where there is a port, a seaside port is there, and this water is entering here, and you can see this wave forming nicely there. Okay, so natural wave. So any kinds of waves will can undergo diffraction. Okay, and light is also a wave phenomena sometimes. Okay, so it can show diffraction, and so with diffraction we can split light like this. This is an actual picture of something called a diffraction grating. Okay, in which there are these tiny holes, tiny slits as we call them, and when light passes through them, it gets split up into what are called spectra. Okay, that's white light, and it's a diffraction grating, and this is the first order of the spectrum. And you see all the colors are there. Here also all the colors are there. There's also another thing that the main part of the light, it continues, but some of it is getting bent out. Okay, there's also more of these diffraction orders. Yeah, those are a little more advanced science. I won't get into that. Now you'll say, okay, fine. I told you can use this to see dispersion. Okay, and you can actually get good spectra from your scale. Now, how can I see diffraction? I don't have diffraction gratings which scientists may be using, but I'll tell you there are diffraction gratings that are available easily in your surroundings. Maybe I don't know if they are so easily available these days. What is this? This is a CD. Okay, and it's a waste CD. So here, what is a CD made up of? So CD is this surface on the CD is actually a plastic, okay, plastic sheet with, when it is carved, the information is carved into it. There's a laser, hot laser, which is used to burn information onto it. Okay, and while burning, what it does is it goes in spirals. So like this, it doesn't like just randomly write everywhere. So it starts writing here and slowly goes outward. Okay, not so fast as shown in this cartoon, but you can understand that it slowly fills it till the whole CD fills. And so what do we get? We get some concentric circles of these kinds of microscopic dots and dashes. Okay, and CD is if you remove the backside or cover, it's actually a transmission grating because it's got these very tiny grooves. And if you take a CD, you remove the backside cover of it carefully, okay, and look through it towards any light source, you should be able to see spectra. And yes, this is spectra taken from everyday lights. Like this is a CFL kind of a lamp, mercury lamp actually, used to be there earlier. Okay, and these are spectra of a sodium lamp and a halogen lamp. And you can see this is the spectra on one side. There's another spectra on that side, which is very far off, so it didn't get captured in my camera. Okay, so yeah, this is the first order spectra, second order spectra, and this is the spectra of sodium light, which is very yellow because it has only yellow. Okay, so it's got sodium gas in it, which emits only yellowish light, and the other lights are not present. So the spectra, basically your grating is splitting up all the light available, and the only light available is yellow. So you get yellow here. Okay, and so this is a very important observation that you can do yourself. Okay, use a CD as a spectroscope. Okay, so this grating was such a great discovery because it gives you most separation compared to a prism. A grating gives you a much better separation of light, and then you can get more details. Now, what was done by a gentleman called Fraunhofer in about 1814, 1815. Sorry, I'm talking about 2 centuries back. So what he did was, he said, let me look at the sun's spectrum through a grating. Okay, so yeah, I mean, you look at the sun all the time. You use the sun's light all the time. But he said, okay, I'm a scientist. Let me look at the sun's light in detail, and he did that. Of course, he did not use like a telescope to look at the sun, or he did not play those games of putting fire to a paper with the sun. What he did was, he took a little bit of the sunlight through what we call a slit. Okay, and he took that light just like I showed here earlier in another picture. So he put a very little slit of sunlight through, and he got a huge spectrum. Okay, it was a very nice grating, so he got a huge spectrum which he could then study. And what he did was, he made a drawing of it. Okay, this is a drawing of the sun's spectrum. Okay, and you have just before I have shown you a good visible spectrum, right? I've shown you this lovely spectrum, which is continuous. It's got nothing, no obstructions, no interruptions anyway. And what did Fraunhofer see? He saw these dark bands, okay, dark lines on it. These were unexpected to him. Okay, and he also noticed that the sun's light is less in red and more in yellow or green, and then less in blue. But that's another thing. But here, what he saw was, there was several lines on it, dark bands, and these are actually called the Fraunhofer spectrum bands. Okay, he couldn't explain them. He was like, "What is happening here? Why are there dark bands on the sun spectrum? When my gas lamp that I use at home, it doesn't have maybe it doesn't have." So he went and he started looking at other spectrum, and spectroscopy was a subject which had already begun spectroscopy. So telescopy is basically means tele means far, and scopy means to see. So spectroscopy is to look at a spectrum. Okay, and people started obtaining various kinds of spectrum and looking at them. So what they did was, sorry, I'll just go ahead. So what they did was, they took something hot, really hot. Okay, high density hot matter is a scientific way of saying this is a glowing bulb. Okay, and they passed the light through a diffraction grating where it got split, and a hot bulb like the incandescent bulb or something like that. Okay, it gives a continuous spectrum. Okay, continuous. There's no obstruction, interruption anywhere. Then they took some hot gas. Okay, some kind of gas, like as I said just now, sodium. Okay, if you take sodium gas into a, put it into a bulb and then heat it up, it gives only yellow light. Okay, that's very special for sodium. Some other gases will give you some other different colors of light. Neon gives you a different color of light. Hydrogen gives you a different color of light. Okay, and what they saw after passing the light through the diffraction grating, this spectrum was gone. and they were seeing only a few special lines of color. They were in that order. Okay, so they were from red to violet. So there's a red, yellow, green, somewhat bluish in this line, but other colors were missing. Okay, they also saw, now this hot gas, the same gas, they cooled down, put it in front of a bulb which was giving continuous spectrum. You see here, this bulb is giving continuous spectrum. Now they put the bulb here, and this gas is cold. Okay, so it can absorb some heat or light, let's say. Okay, some energy can be absorbed by the gas. If it's hot, then it will keep giving out its own energy. But here the cold gas can absorb some energy from this hot source, and then totally this light was passed through an absorption spectrum, through this spectrum grating, and what they saw was just the opposite. Okay, so this continuous spectrum was there, and these lines which were missing from the hot gas which were only seen in the hot gas spectrum, were now missing from the continuous spectrum. Okay, so what they saw was that if there's a gas, it has its own property. Okay, so if you make it hot, it will give out a particular types of light. Okay, and if the gas is cold and some light is incident on it, okay, then it will absorb that type of light and get hot. Okay, so and get more energized, let's say. So if the gas is energized, it will give out some kind of light, only a particular kind of light. No other gas. They later did research with many such spectra, and they discovered that no other gas, no two gases give similar light. Okay, so that was amazing. I mean, they looked at spectra of let's say hydrogen. Okay, hydrogen is the most common gas in the world, and this one, look at this spectrum. This is how the hydrogen spectrum looks like. It's a very thick line in the orangish area. There's a blue line, and these two lines. So this is a spectrum of the hydrogen gas. Okay, this one. This is the absorption spectrum. So cold hydrogen gas and coolish hydrogen gas, and there's a hotter source behind it. Now, what they did was they also looked at other things. Okay, so because the astronomers found this idea. So what they did is they took example, let's say, of the sun, where you saw that these dark lines were missing. Okay, and so there were already spectra of the sun, but they took spectra of some stars. Okay, so this is a kind of a sheet of various types of stars, and these stars have names like O, B, A, F, G, K, M. These are some classifications of different kinds of stars, and each band that you see is of that type of star. So this is O star, this is B stars, these are A type of stars, F type, G type. So they took spectra of stars, and you'll see that O type stars have very less lines, and M type stars have huge number of lines. Right? Our star, the sun, is more of a G5 kind of a star. Okay, and what they did was, now they thought, can this give us an idea of what the star contains? So you see, if the star contains hydrogen, then what is the star? The star is a big ball of gas, okay, hot gas. Now it's more hotter inside, and outside it's a little cooler, and then the light comes to us through this gas layer. Okay, so if the star is giving out all sorts of light, a continuous spectrum, and if the light comes to the hydrogen gas layer, we will get a absorption spectrum of that gas. So if you're seeing these dark bands, which are same as the hydrogen bands which are seen on the Earth. Okay, so we had hydrogen in our labs, we have studied this. So we can now say that the star may have hydrogen. Okay, so you see, you're sitting here on the Earth and you're trying to say what is there in the star, what chemicals are there in the star, what are the gases present in the star. Who has gone to the sun and actually tested that it has got hydrogen? No one. Literally no one. Okay, So it's impossible to do. You cannot go and take a sample of the sun and try it out, see whether it has hydrogen or helium or things like that. I mean, we have not even reached there, but anyway, it's not possible, let alone for other stars. And here there was a way to easily find what are the chemical composition of a star. Okay, amazing discovery that each type of gas, each type of element, in fact, if you make it into gaseous, even iron, if you can heat it up to so that it becomes a gas, it will have its own emission and absorption spectrum fingerprint. Okay, so this is like the fingerprint of hydrogen. These 4 lines represent hydrogen in a spectrum. Now this star has hydrogen, definitely. This line, this line, this line are same. But there are other lines like this line, this line, this line, this line, this line, and this line. Okay. Now they had no idea where these lines were coming from. Then they started looking at other elements. Okay. So as I said, like you can try anything. You can try with whatever beryllium and lithium and then carbon, nitrogen, oxygen, and they found these elements to be present in stars' atmospheres. Really, though in lesser concentration compared to hydrogen. Hydrogen is the most abundant, most that composes almost 99% of the star, most of the stars. And then they saw the other gases were also there, but they were missing this dark line. This dark line did not appear in any earthly spectrum. Okay, so in their labs, they had all kinds of elements that existed at that time. I'm talking about 100 years ago, and they could not find any element which gave this kind of emission or absorption line. And they were surprised. And they said, then the sun must have a unique new element which the earth does not have, or rather which our labs do not have, right? And this was a discovery of a new element, not here, not on the earth, but discovered in the sun. Okay, and so after the sun, it was named as helium. Okay, this dark band led to the discovery of a new element. Later, helium was discovered on the earth. Okay, helium was discovered, helium gas was found in some mines, and there they took that weird gas. Okay, even now helium is not produced on the earth. Remember, helium is a very precious gas. If you are wasting it on helium balloons, etc., don't buy them, because that's wasting helium. So helium is found very rarely on the earth, and it is found very abundantly in the sun. That's what we discovered, and so it was named helium after Helios, the Greek name for the sun. And this is the emission spectrum of helium. And when they found that gas on Earth, they again tested it, and yes, that line was there. It is an emission line, but in the sun it would be the opposite, and they found this band. So what I was trying to tell you with all this is that you can use stars spectra, or rather spectra, the light from stars, to find the compositions. And this is a very good example picture of where you can see now it may probably make sense that these are the names of various things whose lines are found in these stars. Not all stars have everything. So it's like K stars do not have this hydrogen. There's also iron called Fe in chemistry. That's a chemical symbol for iron. There's magnesium, Mg. Okay, there's helium, there's hydrogen, there's cyanide, which is a Cn. It's a compound actually. There's calcium, right? And many other things, titanium, sodium. So there's a huge range of chemicals out there in space in various stars that you can find by studying their spectra. Okay, so either you take a star and directly study its spectrum through a telescope. You take the star's light, get a continuous spectrum. Okay, so star usually gives a continuous spectrum. Now, if the star has an atmosphere, or in between the star and us, there's a nebula, there's a gas cloud, then we can get an absorption or emission spectrum of that cloud. and it can tell us the chemical composition of that cloud. Okay, so this is very much like the fingerprinting of heavenly bodies, the things out there in space which have some chemical composition, and we are getting the fingerprints of them. Okay, we can identify what they are made up of. Okay, so this is the stellar fingerprint, and again, the process is very simple. You take the star, and I showed you a nebula, but it might also be that, you know, there is a planet in between the star and the sun, star and us. Okay, so if we have a good enough telescope, we can even look at the light coming through the planet's atmosphere, and we pass it through a spectrograph, and we can tell now that the atmosphere of that planet has a particular kind of a chemical. In this case, there's just to give an example, because I've told you sodium gives only yellow color light. It gives you only yellow spectral lines. Okay, and so if you see a star and there's a planet going around it, and if you have a good enough telescope to, you know, be able to see the light coming through the atmosphere of the planet, and then you might actually be able to tell, like if it's showing this kind of a spectrum, you compare it with sodium spectrum in the Earth lab, and you know there is sodium in that atmosphere. We don't want to go to that planet. Okay, so of course these might sound like science fiction to you. Those planets are really far away. The star systems are far away. We cannot go there, but we can understand them sitting here on the Earth through astronomy and smart use of physics. Okay, so I now want to bring you to the speciality of today, 6th of October. Okay, and the special day, it's a special day because it is the birth date of a famous astrophysicist and Indian scientist, okay, whose name was Meghnad Saha. Okay, he was born on this day in 1893, and he was the first person to give us an equation. I mean, this is a bit more advanced physics, but this equation, you won't understand anything of it. Even I may not understand part of it sometimes. But the thing is that this equation was allowed us to not just look at the star and the spectrum and tell what is the chemical composition, but it allowed us to reveal many more details about the star, including the temperature. Okay, so we could sit here and tell what is the temperature of the sun. Again, nobody's gone to the sun and taken its temperature with a thermometer, right? So we have done that through the use of good use of light in astronomy and good use of physics. Okay, so we pay homage to the great scientist Meghnad Saha today. This is a stamp which was released on his 100th birthday in 1993. If you are any stamp collectors, go find this stamp. It's a very rare one. Okay, so now with spectrums, various kinds of spectra of stars and other things in space, we are now at this point able to find the temperatures, the chemical composition, the mass and density, the velocities, the speeds of those objects relative to us, and distances of the objects. Okay. Now, just imagine these are different quantities which is extremely difficult to in general to determine for any kind of object. Okay, but now here sitting on Earth, we are able to do that, and we've been doing that for quite a while now. Okay, and that's how we've been able to measure the distances to the stars, to the galaxies, etc. And the picture that I was telling you about, the huge universe with clusters, they've all, the distance to them, the velocity of them have been found by various kinds of telescopes, and that's how we complete the picture of our universe. Now we come to the second bit, the space telescopes. So now in the previous century, all these magical stuff, magical physics, magical science, in a way. I mean, it's like magic up to a limit, unless it's a challenge to understand it, unless you go to a master's level program or something. But that physics was being done with earthly telescopes based on the Earth. Now, in the last century, end of last century, we have put up a telescope called the Hubble telescopes in space. Okay, it was named after Edwin Hubble, one of the first people to tell us that the faraway galaxies are moving at a very rapid speed away from us. Okay, and that's basically explains the, or rather tells us that the universe is expanding. So this telescope was named after him. And then very recently, of course, this has been in the news. So when I was in school, Hubble telescope was my favorite telescope and things like that. So it was my hero telescope. And now for this generation, the Webb telescope is the hero telescope. Okay, but there's a difference. It's not just like I sent a bigger telescope up there. There's a difference, and that's part of the spectrum and the invisible spectrum that some of you have said in the in the chat. So you see, visible spectrum. As I was talking, what we were talking about, the Vibgyor, but there exists many more kinds of light. Okay, so there's a much bigger band of light called the ultraviolet light, and there are X-rays, gamma rays on the more energetic side of light, so more towards the blue, violet, indigo side of light. Okay, after those, and then there are less energy lights like the infrared, the microwave, and the radio light. Okay, I won't go into much detail of these, but I'm just telling you that the Hubble telescope looks across all of the visible spectrum, some part of ultraviolet and some part of infrared. So it is a little better than our eyes. Okay? It not just shows us the visible spectrum, it also shows us a little bit of ultraviolet and a little bit of infrared, which gives us some other information which otherwise we would not have had. Okay, so that's Hubble's specialty. And the James Webb telescope does not really cover this part, the visible spectrum. It's more of an infrared telescope. Okay, so it looks at the infrared light. It can take pictures, it can take spectra of infrared light coming from various things and give us information. Okay, so now with both of these, we have a good coverage over the whole spectrum range. Okay, and so people are going around comparing, like, this is the picture taken by Hubble and see how better the picture is taken by James Webb. Well, they're not actually looking at it in the same way. So this plus this gives the full picture. It's not the top is better and the bottom is top is less good and bottom is better. It's actually the same details, but we are looking at different things. It's like, I had the unfortunate happening that one of my fingers, got hurt and it was paining a lot. It was swollen. So I went to a doctor and he looked at it like this, okay, in plain light, visible light. And he said, I cannot understand what's happened. Let's look at it in X-ray. Okay, then he took an X-ray picture of the same thing. Okay, and then he could tell me that there's a fracture in the finger. Okay, so that's the complete picture. If you look at my finger in visible light and X-ray, then the doctor could tell me what is wrong. But half of, maybe he would not have known. Okay, so X-ray would not show me the skin, and a normal light, visible light, will not show me the bones. So similarly, just take it as an example that Hubble is showing you visible light and James Webb is showing us infrared light. They are both showing us different things. So I'll not go much into this. This I've already covered for you. And one great thing with the Webb telescope is that it can do spectroscopy. Okay, this fingerprinting that I was talking to you about. So it can take light from celestial objects and it can do spectroscopy and it can send the spectrum back to our observers here on Earth. Okay, and it can detect things like carbon, nitrogen, oxygen, iron, etc. to the spectra detectives, as this we can call them maybe. Okay, so there are in fact many space telescopes now. Okay, not all of them are so famous like these two, but there are many, and they are covering from microwaves to gamma rays. Okay, so these are all sorts of telescopes. So Hubble, HST as it is popularly called, JWST is there, but even before that there was Planck and Herschel and Euclid, Cheops, Gaia, Newton, Integral. There's also others by NASA like Chandra, Spitzer, etc., which are there. These are, so you can see there's an array of space telescopes looking at all sorts of spectra. Okay, but they are specialized. So they look at a tiny part of the spectra. Like our eyes are specialized, they look at only the visible light. These can look at various kinds of spectra. And even, in fact, now there are plans for looking at something called gravitational waves, which are not even light. Okay, that's for the future. Quickly give you some understanding of the results which the Webb telescope has given recently. Okay, and again, there's some graph which you may not suddenly understand, but let's still try. Okay, so what is shown here, instead of giving colors like red, blue, green, etc., what we have said is the wavelength. Okay, and earlier I've told you that visible light is up to, this is in these are called microns. Okay, so this is in microns, so this is 3.5 or micron, let's say. So 3.5 is where the kind of the violet usually finishes. Okay, so our Webb telescope looked at Mars. Okay, looked towards Mars, and it was just testing out, because first things you test out with known things. So probably you guys know that Mars has a lot of carbon dioxide, okay, some carbon monoxide, some water vapor as well. Okay, maybe you guys know. So if Webb telescope is running properly, it should look at Mars, and then it should give you a fingerprint of carbon dioxide, right? And that's what we saw. So what is shown here is just the colors, but written in terms of numbers. If you're going to do science, this will be a very common thing to do later, right? So you write, instead of colors, you write numbers. And this is showing the brightness. So this line, basically, it goes across the colors. There's a lot of this kind of color, okay, which is representative of carbon dioxide. Okay, and there's also some water here. So yes, we confirmed that Mars has all that. Now we turn to another planet, but not in our solar system, in another solar system. Okay, so these are some planets which have been discovered by various space telescopes, and they were just waiting for a bigger telescope to actually be able to see through their atmosphere. And that's what James Webb is doing for us. Okay, so we look through the atmosphere of this telescope, through the telescope, but through the atmosphere of the exoplanet, the giant gas planet going around this star called WASP 96b. And this is again the same graph, the wavelength of the light and the amount of light. In this time, we are looking at the absorption spectrum. And what did we see? We saw water, 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 water. And amazing, I mean, it has much less carbon dioxide, but it's got so much water vapor. So it's a planet whose atmosphere is full of steam. Maybe if it's cooler, it could become cloud and it could rain, and then maybe things might get cleared up. So but then this is a great test, right? You're sitting here on the Earth, making a telescope which can peek into the atmosphere of another planet around another star and tell you the composition of the atmosphere. We've also looked at stars, other stars, and tried to see what is around them. And this is another picture of a spectroscopy done in a different way. So instead of just looking at lines, we make images, pictures of a distribution of those kinds of colors, and we add them up. Okay, and we can see that around one of the nebulae called the Tarantula Nebula, okay, people have found there to be hydrogen, which is in the atomic form. So it's not two hydrogen atoms together, it's not bound together. So they found a lot of that. They've also found molecular hydrogen, okay, and they found some kinds of compounds of hydrogen. Just imagine you're sitting here and you're able to see these kinds of details. Okay, now this is possible with bigger and better telescopes. Now, earlier we knew that this can be done, but we didn't have the tools to do it. So now the space telescopes are providing us those tools. Again, the last slide to show the recent, capability of James Webb telescope. So this has also shown us galaxies, and it has in fact found out one of the galaxies which is from which the light takes 13 billion years. Okay, so billion means you have to put how many? To put 9 zeros after 130, after 13. Okay, so that many years that light takes to come to us, and from that galaxy it has been able to show us there is oxygen, hydrogen, neon, and such chemical composition of the galaxy. This is mind-blowing, and I think just a few years back I was doing such experiments with the light in in my office room here, and today we are able to see such amazing results from James Webb Telescope, which are based on the same technique which I was trying to understand in my basic lab. So that's why I always tell you that keep looking around you. There is science to learn and discover, but you have to have